quantum information theory. So it's really exciting to be a part of this development. Okay, so now I'll sort of get into the physics. So this is the summary. If you want a 2-slide summary to take away from this talk, sort of this is it. That there was an apparent paradox since 1975, and a few years ago, people have made progress on it and showed that black holes are in fact like every other system in the universe, and that the laws of physics that govern black holes are also reversible in time. Okay. All right. So before we talk about quantum mechanics and stuff, we should talk about classical mechanics. So if you take a bird's eye view of classical physics from a theoretical point of view, there are really just two fundamental theories. There's two theories. One is Maxwell electrodynamics, which was discovered by Maxwell in 1860s or 1870s. I don't remember. The other one is Newton's theory of gravity, which is older. But its modern version is Einstein's theory of gravity. It's also called general relativity. Okay, so we have electromagnetism and gravity. Those are the two forces, and these theories sort of describe the classical versions of these theories. What I mean by classical is classical as a counterpoint to quantum. So in classical mechanics, there are no probabilities. You're given the initial state of a system, let's say the position and velocities, and the equations of motion of the system allow you to completely determine the system at later times. So given x of 0 and v of 0, you can compute x of t and v of t at all times, right? Okay, so what are the kind of things we solve for? So the first thing you do is, you solve for the field of a point charge. Like even in the JEE syllabus, we know that there's a point charge or a point mass, and it generates a potential. There could be a gravitational potential or an electromagnetic potential, depending on what the theory you're considering. So phi is the potential, and it satisfies a differential equation. It satisfies a differential equation of this type that I have written in terms of these partial derivatives. The point is that the C constant is just some charge or some mass. For the case of Newton, it's mass. For the case of Maxwell, it's charge. And the solution to this is the famous 1 over r, potential of point charges or point masses, right? Okay, so what is a black hole? Essentially, a black hole is a point mass in Einstein's theory of gravity. So forget not the Newtonian theory that you studied in your 11th class, but you take Einstein's theory of gravity and consider a point mass in it, and that's a black hole. So it is the simplest kind of thing that could exist. And indeed, this solution to Einstein's equations that describes a point mass has been known since the year 1916. So that is more than about 110 years old. And the solution was found almost immediately after Einstein published his paper on general relativity. And it's known as this guy, Schwarzschild, the Schwarzschild solution. So what does it look like? So what does a black hole described mathematically look like? So analogous to the previous differential equation that we saw for phi, Einstein's equations in this special case give us a sort of a simple equation for g. So g is some function now. Think of it as the analog of phi. And here is a differential equation. R dg dr is g minus g squared. So that's it. Like that's what Einstein says. The first thing to note about this equation that it's nonlinear. It's nonlinear because it contains this g square. It's not just a linear differential equation. So that's the first point of difference. As opposed to Maxwell's equations, Einstein's equations are nonlinear. Okay, but it's fairly easy to solve it. It's a very simple differential equation, and you get g of r is r over r minus r star, where r star is a constant of integration. Okay, it's a first order equation, so you get a constant of integration. It's just fine. Now, what is this r star physically? This r star is proportional to the mass of the black hole, which is the same as the mass of the star that would have formed the black hole in the first place. So it's related to 2 times the Newton's constant times the mass. Okay. Now, if you go to large R, so this point mass is sitting at R equal to 0. So you're at R equal to 0, and now you go to very large R. So you're very far away from this point. So you're very far. And when you're very far, you can do a simple Taylor expansion And this G of R will have an expansion in powers of 1 over R. So the leading term is 1, because as R goes to infinity, this function approaches 1. And then there is a correction, this 2gm over R. And note that this 2gm over R is precisely this Newtonian potential. Right? So this G of R is a fancier, souped up version of this Newtonian potential that you have studied in 11th class. Okay. Okay, so are there any questions? Maybe this is a good time to take a couple of questions if people are still following, or is it?
Excuse me, sir.
Yeah.
Is the 1 by R solution the only solution of that derivative?
I can't hear you.
Is the 1 by R solution the only solution of that derivative equation, sir?
Of that previous one.
Yes, sir.
No, it's not the only solution. It's a second order equation. So you will also have a solution that's growing at infinity. So that is an unphysical thing where you have a point particle which is sourcing a force which is growing with distance, instead of falling with distance. So, we're supposed to reproduce the 1 over R square behavior. And if you had the other solution, like you wouldn't recover the 1 over R square law.
So this is the only physically acceptable solution.
Yeah, this is the physically acceptable.
Thank you, sir.
I think there were some other questions. I can't read the chat, so it's probably better if people just ask, unmute and ask. This, don't worry about it if you don't know what this is. This is the so-called delta function. It is just supposed to represent the fact that there is a point charge at the origin. So this is some infinity, because if you have a point charge that is strictly at a point, its density is infinite. So don't worry about it. Like this equation is basically the equation that says del dot E equals Q over epsilon naught, or the integral of the electric flux is equal to the charge enclosed. It is basically that equation. This is just Gauss's law. Yeah, this 3 is a three-dimensional delta function, but it doesn't matter. If you don't know about it, it doesn't matter. Okay, all right, very good. So now we have this black hole solution. It is given by this function g of r, but what does it physically mean? So to understand what a black hole really does, we must talk about the trajectories of light rays in the presence of a black hole. So what happens to the motion of light? So before we do that, let's review the trajectories of light rays in empty space. So empty space is just described by special relativity. So let's just focus on light rays. So let's say you are an observer sitting at a point at the center of the universe, and there are light rays either coming towards you or going away from you. So here is simply what it would look like. So in these diagrams called space-time diagrams, time is vertical and space is horizontal. So let's say I'm located at the center here at r equal to 0. And time is being measured in seconds, and the distance is being measured in light seconds. So in 1 second, the light moves by 1 light second. So these are 45-degree lines. So they are the red lines that are sort of coming in to the point r equal to 0. And there are these blue lines that are going away from r equal to 0. Okay, it's very simple. So they're just light rays moving at constant speed, at the speed of light in vacuum. There is nothing else. The red lines sort of come and hit me, and the blue lines sort of go away from me. Okay. All right. So now let's look at the same thing in the presence of a black hole. So in the presence of a black hole, here, the black hole is at r equal to 0. So it's a point mass, like we said, Einstein gravity. It's a point mass in Einstein gravity. And this thick black line is the locus of that point mass. And these red light rays are the inbound light rays. So these are the light rays that are coming in towards the black hole, and nothing special happens to this figure on the left. So that is the same as before, nothing happens. But to the blue light rays, something very drastic happens. So if you're very far away at large R, these blue lines approach these 45-degree lines. So that means that very far from the black hole, the gravitational field or the gravitational force is very weak. And effectively, the light moves like it was flat space. So there's nothing going on here. But what happens is that as you come closer and closer to the black hole, there are some blue lines that are actually wanted to go out but couldn't go out and fell into this thick black line. So in particular, this line here that I'm highlighting and this one. So even the light rays that sort of would have gone out in the presence of the black hole kind of fall in towards the center. That means that there is a region which is in between this black line and the green line from which light cannot escape. Okay, so there's a finite region, radius around the black hole center where light cannot make it out very far away from the black hole. So it's kind of trapped. Okay. I think there were a few questions in the chat. Maybe if somebody is moderating the meeting, one can read a few. Yeah, I haven't mentioned that. So please ask questions only about things that I have mentioned. I probably don't want to answer questions that involve terms that I have not used. Well, so I have just told you the result. I have not given you the equations behind it. This is what comes out of the analysis. I'm telling you the result. So this is the result of studying how light moves in the presence of a black hole. I mean, of course, this is only a 40-minute talk, so I cannot give you all the details, but this is what it does. So hopefully the final picture is clear, even though I have not derived it. Okay. So let me give you some more equations actually. So these are the equations that govern these blue light rays. So d tau is this coordinate that is vertical, and r is the radial direction. So this r star was this constant of integration, and now we have some different functions here. Okay, so d tau 1 minus r star over r is dr1 plus r star over r. If r was big, then these two terms can be ignored, right? R star over r would be very small if r is big, and similarly here. So just get d tau equal to dr, and that is a 45-degree line, right? The time goes up by 1 unit, r goes up by 1 unit, that's over here. On the other hand, note that if r is equal to r star, then the left-hand side is 0, right? So that means that this dr has to be 0, which means that r is not changing. So that's the green line. Okay, and if r was less than r star, similarly, you can see that dr must keep getting negative. So that's one way to see why it has to go in. But anyway, so I'm just trying to show you some equation that there is some real math behind all of these things. So the green line is called the horizon of the black hole. The black line is called the singularity. So singularity, horizon, and in between the singularity and the horizon, we have what is called the black hole region or the black hole interior. Now let's get some sizes. So for the sun, if m is the mass of the sun, then this horizon location, this r star, is only 3 kilometers. And if the mass of the black hole was the mass of the earth, then this horizon would only be at like 3 millimeters or 1 millimeter. So essentially, like to make the earth into a black hole, you have to squish it so that it's smaller than 1 millimeters. So those are very extreme conditions. Like you have all of the earth, which is 6,400 kilometers in radius, you have to shrink it down to 1 millimeter, and only then does it become a black hole. Okay, so the sun and the earth currently definitely do not fit this description. So they are not black holes. Here is a different picture. So here is what I was drawing before. So here the red line is the horizon, the blue is the singularity, and the black region is the black hole interior. And the same figure on the right is just a 3D version of the figures that I was drawing on the previous slide. So this orange thing at the bottom is a star, which is growing small as time goes on. So time is always vertical. And at some point it becomes very small and you get this horizon, black hole, and blue line at the center. And these yellow cones are the light cones. So the light is constrained to move within these yellow cones in the forward light cone, so called. And you see that in the black region, these yellow cones are completely tipped towards the blue line. So that is another way of representing the fact that light cannot escape. Uh, anyway, and of course, I want to point out that there is experimental evidence that black holes actually exist in the universe. This is not just theory talk. This is a signal, the orange line is a signal that is captured by these LIGO observatories when these two black holes collide. So they orbit each other, they emit gravitational waves, because of which their orbit radius becomes smaller and they eventually collide and merge. And this merger process creates the signal that we have detected on Earth. And astrophysically, this I have already said, a black hole is formed when a star becomes very small due to gravitational contraction. And the first analysis of these gravitational contractions was done by Oppenheimer and Snyder. Oppenheimer is the same and Oppenheimer who was the chairman of the atomic bomb later. Okay, so far we have discussed the classical black holes, and we have been studying solutions to Einstein's equations and particle propagation along definite trajectories. Now I want to move on to quantum black holes. So I will discuss some features of general quantum systems that we will need. But I think I will skip over some of this discussion because I think I cannot do complete justice to this. So we need to know something about quantum mechanics. But okay, this is again a good time to stop for some questions. Yeah, yeah, yeah. Well, I have not talked about observers. I have only talked about these light rays. So this is an equation for the light ray. And dr equal to 0 when r equal to r star means that the light ray is this straight, this green line, or in these pictures it's the red line. Okay, so in this picture, this yellow cone is sort of the combination of this blue line here and the red line here. So if you think of the blue and the red line together at one point, all actual observers are constrained to move within that cone. So because light moves the fastest, nothing can move faster than the speed of light. So in some sense, if light starting in this interior black region cannot escape, so if light starts in the black region and cannot escape, then no one else can escape because everybody else is forced to be on the inside of the light cone. Light is at the boundary of the yellow region, and actual particles like us, we will be inside the yellow region, like strictly moving inside those cones. Okay, what was the other question? Wavelength. Wavelength. No, I didn't really use the word in infrared. Well, no, it will not be independent of the wavelength. We are working in an approximation. I mean, we are talking about light rays, right? So in optics, the geometric optic approximation, these light rays are only valid if the size of objects that you have around are much larger than the wavelength of the light. So this black hole has a size, this R star. So it means that if you make a wavelength, light of wavelength, which is comparable to 3 kilometers around the sun, it will undergo significant distortions from the gravitational field of the sun, right? Then the wave nature will be important. But we were just talking about light rays, and that just the usual approximation that unless there are apertures uh, in your double slit or something that are comparable to the wavelength of the light, nothing special will happen and light will just move on sort of straight lines. Okay. Okay. All right. So I guess this part, the next maybe 5 to 10 slides will be for people who know some quantum mechanics. So please bear with me. I couldn't really do justice to it without uh, going through this. So quantum mechanics, describes systems, and the idea is that the state space, so the set of states of a system, form a vector space. So a simplest vector space is two-dimensional, and an electron spin is a spin-a-half particle. It can be spin up or spin down, and that forms a two-dimensional vector space. So the state space of a spinning electron is two-dimensional. Now, this H is the so-called energy of that system. And in quantum mechanics, energies are matrices. They're square matrices having a size equal to the dimension of this vector space. So we had a two-dimensional vector space. So H is a 2 by 2 matrix, and it has to be a so-called Hermitian matrix. It doesn't matter. So it just looks like some matrix like C minus C, A minus IB, A plus IB. I is the square root of -1, and A, B, and C are real numbers. Okay. Uh, but what happens is, now let's say you have two spinning electrons. For example, you can have the hydrogen molecule, right? There's H2. So one hydrogen atom has one electron and the other one has another electron, and they exert some forces on each other. They interact with each other. What happens is then that the energy of the system is a function of the state of the combined system, right? So what this equation is saying here is that the spins of the two electrons, S1 and S2, their energy will be the lowest if they are anti-parallel, right? Because it's a dot product of two vectors of fixed length. So a dot product can go between -1 and 1. So if they're parallel, it will be the largest energy. And if they're anti-parallel, it will be the smallest energy. Okay. So this is what I'm trying to say. The system has the lower energy when the spins point oppositely. Okay. And this is a consequence of there being some kind of a force between the two particles. They're interacting somehow. Okay. And if you actually work it out, if you take this Hamiltonian, the energy being spin vector times the spin vector, the lowest energy state is actually not this up down and down up separately, but this linear combination. So in quantum mechanics, we can have linear combination of states, and the ground state is up down minus down up divided by square root of 2. The one with the plus sign has a higher energy actually. So that's the surprising thing. So this force between the electrons uh, kind of correlates the two electrons together in this particular fashion. And note that this is not a simple tensor product state. This state cannot be written as a product of the state of the first electron times the state of the second electron. Essentially, if you take this equation at the bottom and try to solve for alpha, gamma, beta, and delta to get this 1 and -1 coefficient, you will fail. Like this will not work. Okay, so this is what entanglement means. So states are entangled when there are forces between particles and we have these states that cannot be factored out. Okay, so I hope this part at least is clear to people who have taken some quantum mechanics. Now I'm going to skip over this stuff. I think this is maybe too advanced. Okay. Okay, so now let's come to what we have in Hawking radiation. So we know that in our universe we have so far been talking about light, and we have been talking about black holes, right? We were considering the classical motion of light rays in the presence of a black hole. And so we should now, when we want to go quantum, we should consider the quantum theory of light. And the quantum theory of light goes by the name of quantum electrodynamics, or QED. Okay, so what is QED? A QED is one example of what is called a quantum field theory, or QFT. These are just names. Okay. Now, this QFT is nothing but a quantum mechanical system consisting of an obnoxiously large number of springs on particles. So possibly with some small anharmonic terms. So just imagine not one particle, but like millions and billions and trillions of particles. Okay, and they're all interacting with each other. It's all kind of a very messy system. So that's what QFT describes. And how large is obnoxiously large? Basically, there is one harmonic oscillator for every spatial point x vector. So, we live in a three-dimensional space. Imagine putting like a lattice. So imagine that your space-time was a grid, and at each grid point, there is one harmonic oscillator. So the picture looks kind of like this. So these solid points are like space-time points on a grid. And imagine like there is a particle at each of these locations. There is some degree of freedom at each of these locations, and they're interconnected by these springs. So it kind of looks like a mattress with various springs sort of connected to each other. Now, it should not come as a surprise that the ground state of such a system is entangled. I mean, already when we had just two electrons, talking to each other, the ground state was entangled. And in this system, there is also going to be a lot of entanglement. That is, if you look at, for example, is the state of this particular object here, is it independent of the state of its neighbors? It's not going to be independent because there are springs that are connecting it to its neighbors. And if uh, its position of one atom was very different from the position of the next one, that spring would be stretched by a lot, and that would cost a lot of energy. So the system tries to minimize its energy, go to the ground state. That means the motions kind of lock with each other to some extent. And that gives rise to entanglement in the ground state of a QFT, including QED. So QED is just a specific example of a QED, which is the theory of light interacting with electrons, interacting with gravity, and so on. Okay, so here is a reminder from before. We had these red light rays that were going in, and there was this region between black and green from which nothing could come out. Now, what this means is that if I am an observer sort of far away, like on this blue line, this is my lab and the time trajectory of my lab, I can never get signals from this region between the black and the green. So the interior of the black hole is completely causally disconnected from my world line, right? I can never receive signals from it because light was just stuck inside. So now we have this field floating on the spatial direction. So I told you, imagine that the space is a grid. So we have these grid points, 1, 2, 3, 4, 5, and so on. This observer here in my lab can only see particles 6, 7, 8, 9, 10, and so on. He can never see these 5 particles that are inside the black hole. But the quantum state is still entangled between all these particles. Okay, so this is essentially the derivation of the Hawking effect. So since no light from the region behind the horizon ever makes it out, the experimentalist does not have access to the subsystems behind the horizon. And these subsystems are these points 1, 2, 3, 4, 5. So what this means is that the state that the experimentalist would measure would be a noisy state. It is noisy because you are erasing the correlations with what was inside the black hole. So that is the source of the noise, because you cannot see the stuff behind the black hole, but the stuff outside is still correlated with it. Okay, so here is the paper that Hawking wrote in 1975. And this is a beautiful formula. So this shows that this stuff that, okay, that's a good question. Somebody is asking, what does noisy mean in this context? Noisy just means that if you try to sort of collect the Hawking radiation and try to sort of measure what its past state looked like. Let's say you collect some Hawking radiation outside and you try to figure out from that what the initial star that underwent the collapse to form a black hole looked like. The Hawking says that you will not be able to derive any such information from it. Does that make sense? So, essentially, if you had a coherent object in the beginning, then you sort of lose all the information that was in the object, and you get all this uh, all this sort of noisy Hawking radiation. So here is a formula for the temperature of the black hole. So m is the mass. So that's a parameter. Like for the sun, there's a mass of the sun, and for the Earth. But you see, it has Planck's constant. That's quantum mechanics. It has the speed of light, so there is some relativity going on. There is G, right? So G is gravity, and Kb is the Boltzmann constant. So this formula kind of captures the fact that I was telling you in the beginning that this subject is sort of involves a lot of different fields of physics. The quantum mechanics, relativity, gravity, thermodynamics kind of all come together. And this symbol means the mass of the sun. So if the mass was the mass of the sun, the temperature would be 10 to the minus 8 Kelvin. So it's very, very cold. Like it's not a very big temperature. It's like some very, very small temperature, but nevertheless, it's non-zero. It's basically small because the Planck's constant is very small. So it's a quantum effect. You see, if you were purely within classical mechanics, h bar would be zero, and then this temperature would be zero. Okay. So in other words, to an outside observer, it is as if the black hole is emitting blackbody radiation at this temperature. Okay. So the wavelength of each emitted particle is of the order of the horizon radius. So this is a huge wavelength, which is 3 kilometers for a solar black hole. And because the temperature is so small, the energy carried by each emitted particle is also very small. Like kBT is like 10 to the minus 30 joules. So, and one particle is emitted every time interval of 3 kilometers over c. So in a time that it takes for light to cross the horizon of the black hole, it emits one particle. And this also means that the black hole will eventually disappear since it is losing mass. And the time for a solar mass black hole to evaporate is 10 to the 67 years. Now, this is a ludicrously large amount of time. This process is very slow. It's a very cold and very slow process. And a reminder is that the age of the universe is only 10 to the 10 years. Whereas if you let an isolated solar mass black hole sit there and let it evaporate by the Hawking process, it needs 10 to the 67 years. It's just unimaginable how long this process will take. But we are not doing practical experiments. Uh, we are um, we are just thinking about things theoretically. Okay, so after the black hole is gone, so now let's again recap. So imagine that a black hole is formed from a star, and that initially we had very precise information about the position of velocity of every particle in the star. So in short, we know all there is to know about the initial state, and the entropy is zero. The entropy is a measure of how much noise there is in the system. And Hawking then thought about the very distant future, a time when the black hole has completely disappeared and has left behind a cloud of black body radiation. Okay, so now the black body radiation has a non-zero entropy, right? Because it has a temperature. And if you remember the formula, the black body radiation at a certain temperature has an entropy given by the thing proportional to the Stephen-Boltzmann constant and so on. So the process of black hole formation and subsequent evaporation produces entropy. So this is just another way of saying that this process is irreversible, or which is the same thing as saying that the outcome is noisy, whereas the input was not very noisy. It was completely noiseless. Okay, so here is another of Hawking's papers in which he was discussing this breakdown of predictability. Breakdown of predictability is again a same word that says if you lose information as you're evolving in time, then you cannot evolve backwards. This is also a paper from 1975. Okay, so this is what is happening. You have a star at initial time, it collapses to form a black hole, and you have this Hawking radiation that is left at the end. Okay, so now some of you might object to this. You can say, okay, we studied a law in thermodynamics. It's called the second law of thermodynamics. And it says that the entropy always increases. Okay, so what is going on? Why am I telling you that the black hole producing entropy is a problem, whereas the second law is a law. And so what is happening? I mean, the point is that the second law is not really a law. So you should actually be very careful in using that terminology. Here is typically what happens in the second law of thermodynamics. Now, forget about black holes. Just imagine that you have a gas of particles and you start those particles out in a well-defined region of space and with a well-defined sort of momentum. So P is momentum. So it's a well-defined sort of distribution. So it's very tight. Now, if the motion of these particles is kind of complicated, what will happen as time goes on is that this phase space that is occupied by the gas will get more and more complex as time goes on because it's just undergoing some random motion. I mean, this is not even capturing it properly. This is just to give you an idea that you get all these sort of tendrils, fibrillous structure from the initial sort of configuration. Now, the point is the area of this object is actually preserved under time evolution. So it's not becoming larger or anything. But it does become large if you put on sort of blurry glasses. Like if you were only able to measure the position and momentum of particles to within a precision of these green balls, then what you would do is you would try to cover this amoeba shaped region with these green balls, right? And the area of the green balls is more than the area of the underlying amoeba. And as time goes on, you need more and more of these green balls to cover the amoeba because it is becoming more and more tentacly. So that is the essence of second law of thermodynamics. It is somewhat a coarse-grained entropy which increases. The actual underlying state of the system does not become very random. Okay, so that's why it's a problem. Anyway, so there's a tension between fundamental physical principles here, and big revolutions in physics happen when well-established principles run into contradiction with each other. I mean, a classic example is the incompatibility of Maxwell's equations with Newtonian relativity. And so that, this incompatibility of Maxwell's equations with the Galilean relativity led to special relativity that Einstein discovered. Or the incompatibility of the equipartition theorem with the finiteness of energy led to quantum mechanics. Okay, so some progress has been made since 1945, and my view is that even though we made some progress in 2019, we are still far from fully understanding the quantum nature of black holes. So the current almost universal belief is that entropy is in fact not produced when a black hole forms and evaporates. So there are some subtle things that Hawking had missed. And this comes from very indirect reasoning, crucially using string theory and what is called the ADS-CFT correspondence. So let me just use it as jargon and not explain what this is because it will take us a long time. This is simply saying that black holes are just like any other system we learned about in undergrad. But Hawking definitely did not make any technical mistakes in his calculations. So this implies that there must be an implicit assumption that he made and which we must give up, right? Because his paper is correct. Like if he has some assumptions, and if you believe those assumptions, there is not a technical error in the paper that you would say, oh, this is wrong. So there is something very subtle. So here are two implicit assumptions we made. One assumption is that these harmonic oscillators on the two sides of the horizon, on the inside and the outside, are smoothly connected. That means there is a spring that connects the objects on the inside of the horizon to the outside of the horizon, right? Which is what is causing the state inside and the outside to be correlated in the first place, right? If I cut all the springs at the horizon, then the system inside and the outside are not talking to each other, and then there will not be a paradox. So this is a secret assumption. The other assumption is the following one, which is that the harmonic oscillator at each spatial point x has its own individual state space. is what I said. Like in quantum field theory, you typically assume that there is an independent oscillator at each spatial point x. So this is also an assumption. This is the so-called locality principle. Okay, so let me skip over this. So in this work that we did in 2019, we basically said that it's this the second thing that we must give up. That in the presence of a black hole, it is no longer true that each spatial point is an independent harmonic oscillator. This means that some of the harmonic oscillators inside the black hole might be phantoms of others that are very far away. So the structure of this theory is not so simple as in the absence of a black hole. So the idea of giving up the locality principle is not new, but we performed some simple calculations in a toy model that supports this viewpoint. Okay, so here is a picture that you might have. So you have a black hole that's emitting some radiation, and somehow there are these tiny objects or wormholes. This is a cartoon. This is not supposed to be a real physics picture that what happens in the universe. But it's supposed to convey that the interior of the black hole is not completely independent from the Hawking radiation particles that are outside. Okay, so here's a summary. So I'm going to finish in the next 2 minutes. A point mass in Einstein's theory of gravity is called a black hole. In the presence of a black hole, there is some region of space such that light emanating from it always falls towards the point mass and cannot escape to infinity. And since an outside experimentalist cannot see this region of space, they see the quantum state of photons as being this thermal, noisy, so-called density matrix. And a naive view suggests that this leads to entropy production. And however, in the light of modern developments, this viewpoint is not correct. And the resolution is to give up the locality principle. This means that quantum mechanical subsystems located at faraway points in space are not completely independent. Okay. So, in other words, quantum mechanics is more fundamental than quantum field theory. After all, this information preservation happens in quantum mechanics. It's there. And a QFT is just a specific example of a quantum system. Okay. And there is no notion of locality in a general quantum system, but there is a notion of unitarity. Unitarity just means this reversibility in time. So, that is the perspective that we have, that it's the positions and what is nearby to what gets messed up. So the distances get messed up, but it's still true that motions can be run backwards in time. So I would just like to end by saying that there are perhaps two other things in the universe that we know even less about. One is the nature of the Big Bang singularity, and the other is universes with accelerated expansion like ours. So we hope that maybe research in the future years will shed some light on these questions, and also the black hole singularity. Okay, let me stop there. Sorry for going over time, and maybe we can take some more questions. I think there were some questions that were coming in the chat. Maybe now I can see. Okay, yeah. Yeah, okay. So let me see here. Yeah. Yeah, okay. So the first question was, why are we using two-dimensional matrix for analysis? So that was just a example of a Hamiltonian. It was not supposed to capture the general case. So that is the simplest quantum mechanical system. So that's why I started from there. So S is the spin. So S square has units of energy. Sorry, I should have put a constant in front of S square. So the energy was not S square, but it is some constant times S square, and that constant makes up the units. But the important point is that the physical quantity that is proportional to is the square of the spin, or more precisely, the dot product. So a quantum black hole is basically what I tried to explain. A classical black hole is a solution to Einstein's equations, in general relativity. Whereas a quantum black hole is when you try to merge that general theory of relativity with quantum mechanics. In particular, you try to treat the photons and the electrons and the gravitons sort of quantum mechanically, not as classical objects. So noisy, I think I already explained what it means. Measurement is just like measurements in the lab, like you would do. I mean, if you are a person far away, you have some photo detectors. You can set up measurements of the Hawking radiation. Okay, so how are the inside and the outside particles entangled? So this is what I was saying, that in some sense, this is an assumption, but it's a very valid assumption because you see the space-time geometry, which is described by this function g of r, is smooth as you cross r equal to r star. Right? There was nothing weird that is happening at the horizon. So right now, if there is a black hole horizon at my location, I will not be able to tell by doing any local experiments. So it makes sense that if I have these little balls in that mattress picture everywhere, both inside and outside the horizon, that there are springs that also connect the balls sort of inside and outside the horizon. So the existence of those sort of tiny springs causes that uh, state of the photons to be entangled across the horizon. Yeah, so how the radiation is able to escape the event horizon, it's because of quantum mechanics. So this initial pictures that I showed you where light does not escape and there's a black region is completely classical, which follows from Einstein's equations and how particles move in a geometry. But the point is precisely when you take quantum mechanics into account, black holes are no longer black, like they emit stuff. Forces are effects. Okay, this is the answer, I think, to the previous. Okay, I can share the slides with the organizers and but I think a version of this also exists on my website, so I think you can see it there. Okay. Okay. I mean, books, I think this guy at Stanford, Leonard Susskind, has some books called The Theoretical Minimum, which is like a sequence of books he has written, which sort of introduces physics at an undergrad level. So if you want to sort of read more about quantum mechanics and each of these pieces sort of separately, there's a series of books. It's just called The Theoretical Minimum. So let me type it here. He also has some other books which are okay. I think the math courses, you just need to take it while you're doing the physics. So I don't think at some point, the math training has to happen within the physics courses. I mean, probably linear algebra is something you want to take, but other than that, uh,
Sir, you said the fact that black holes aren't really that black. While we were discussing this before the talk, we joked about it that black holes are actually brighter than our future.
yeah.
And sir, I had a little doubt about quantum field theory. That you
Mhm.
said that at every lattice point there's a oscillator.
Yeah.
But don't we say that when there are many quantum particles and when we are talking about a macro object, that we can ignore the quantum effects? Like when we're talking about a cat, we're no longer thinking about it as a
Yeah.
quantum particle.
But these effects that we are talking about are precisely at the subatomic level. Like all this entanglement and so on, you will have to measure it with that precision.
So they're happening at the subatomic level, but they're showing up at the macro level as well.
In some sense, yeah. Yeah. But you see that this Hawking radiation is very cold. So in order to measure such a small energy quantum, you will have to be do a very precise measurement. Right? Like the energy of each particle that was coming out of a solar mass black hole was 10 to the minus 30 joules. So
Very
experimentally, it's very hard to measure that. So these are all quantum effects that you can measure, but it'll probably be very hard to measure them in an actual physical experiment.
perfect. Thank you, sir.
Okay. Are there any other final questions? Okay, so looks like we're good. Yeah. Okay. Okay. Yeah.
Sir,
Thank you for the.
I have one doubt. Sir, why neutron star collapse to form black hole?
Sorry, say that again.
Sir, why neutron stars when they're revolving they collapse with each other and form black hole?
Yeah, that can happen. I mean, I don't understand the details of it. It's not something I have studied, but
Sir,
people
what
have
is the
observed.
reason behind that?
The reason behind it is essentially that, for example, for the sun, right? Like typically what happens is, now I'm not an expert on this, but so first of all, this hydrogen and helium in the sun will run out, right? Right now, what the sun is doing is burning hydrogen to make helium, and that is creating some outward pressure. So then it will run out of nuclear fuel. At some point, the star starts to collapse, becomes compact, and at some point starts to be supported by what is called the degeneracy pressure of electrons. At that point, it's a white dwarf. So what a degeneracy pressure is, you think of the whole star as a zero temperature gas of electrons. And electrons are these fermions which obey the Pauli exclusion principle. So because of electrons don't want to be on top of each other. They resist the inward force of gravity. But that can also only happen if the mass of the star is sufficiently small. So if you had a mass of the sun, if you had a star which is like 3 times the mass of the sun, it cannot be supported by degeneracy pressure. And similarly, there's a limit for neutron stars as well. So that's not very well understood because the equation of state for neutrons at such high density is not very well understood. But the point is, if you have like a 10 solar mass, object, it's very likely that it's going to form a black hole. Just because
Thanks.
there are no outward sources of pressure to balance gravity eventually.
Sir, I wanted to ask that whatever theories which you work on, say for example for black hole, the information that you verify it with, I guess it must be some maybe some information from telescopes that are present on Earth, or some, like, I don't know how you detect Hawking radiation, but isn't that something which left that particular black hole years, many light years ago, and it reached to us now. So, like, how do you deal with the time lag? I mean,
Well, so let me say one thing. Hawking radiation has not been detected. All this stuff that I'm talking about is purely theoretical and maths.
okay,
Okay. So what has been detected though is something similar, which is gravitational waves that are emitted when two black holes collide with each other. So that was this yellow signal that I was showing. But the point is the kind of question you are asking is encoded in that signal. Because you see that signal has wiggles and some oscillations, and it's not a random signal. So if you measure those wiggles very precisely, you can tell a lot of information. You can tell what was the initial masses of the two black holes. Like one was a 40 solar mass black hole, the other was a 60 solar mass black hole. You can tell what their relative angular momentum was. You can tell how far away they were. So all that information, even though that signal left the black holes very long time in the past, like hundreds of light years in the past, but that information is still there in that message that was emitted at the time of the collision.
yes, sir.
So there was a collision that happened sort of hundreds of light years ago, when Earth had probably not even formed and humans were not even there on Earth, and somehow we are able to the Earth is able to evolve some life, and intelligent human beings can build a detector that can measure that signal. So, but that information sort of propagates undistorted on that waveform. It's like a radio signal, right? We transmit radio from one place to the other. It can go undistorted for some time. So these gravitational waves can travel very long distances in the universe without getting distorted.
Okay, sir.
Sir, this is more of a personal question, but like we're as undergrads, how can we go into research except for the along with the textbook methods, like doing some research project with the professors or reading research papers? Is there some pro tip now that you're on the other side of things?
Well, I think, well, there are definitely online resources like this theoretical minimum and stuff that are available. But I think that when I was in IIT Delhi, the theory department was maybe a bit behind, but now there are two very young faculty that have joined just 2 years ago. There is Tarun Sharma and Sarthak Parikh.
Yes, sir.
And I think those are very like young people, roughly my age, who would be, I think, happy to talk to interested people. So you should make use of the resources that are there in IIT Delhi. I mean, these people have done their PhDs at some of the best institutes and done postdocs also, and they are very much plugged into the cutting edge of research in high energy physics, in string theory and quantum gravity.
Thank you, sir.
Yeah. Okay. Thank you. Okay. Bye.
Thank
Bye.
you, sir.
Thanks.
Bye bye.
Bye.